Welcome to the HPC Best Practices webinar series. This series is brought to you by the IDEAS Productivity Project, which is part of the Exascale Computing Project, ECP for short, of the United States Department of Energy. I'm Osni Marquez from Lawrence Berkeley Laboratory, and will be the host for today's webinar, Writing Clean Scientific Software. The webinar will be presented by Nick Murphy. Nick is an astrophysicist and research software engineer at the Center for Astrophysics in Cambridge, Massachusetts. He went to the University of Michigan as an undergraduate, then to the University of Wisconsin for graduate school in astronomy. Most of Nick's research has involved simulating plasma processes in the solar atmosphere, and he's one of the core contributors to Plasma Pi, which is an open source Python package for plasma research and education. Nick co-founded the American Astronomical Society's Working Group on Accessibility and Disability, and is now a member of the American Physical Society Division of Plasma Physics, Diversity, Equity, and Inclusion. We have issued more than 350 tickets for today's webinar. We never know how many people are going to show up at the end. And all attendees have been muted upon entry. We'll receive questions through the Zoom chat and also Google Doc, whose address I'll paste in the chat momentarily. We have asked Nick to add breaks during his presentation so he can respond to questions that come in. However, for the sake of time, we may have to delay questions to the end. With that, Nick, I'll stop my sharing and then you can take over.
All right. Okay. And this is showing up okay?
Yes.
Perfect. All right, so I'll get started. First of all, thank you for the very kind welcome. I'm a huge fan of this webinar series, so thank you all for being here too. I really appreciate it. I'm excited to share suggestions with you on writing clean scientific software that I've compiled over the last few years. These suggestions are mostly intended for students and scientists who have some experience writing code, but who have had to learn how to code mostly on their own. These suggestions are especially for those of us who, like me, have never taken any classes on software engineering or had any formal training on how to program. I do have to thank a number of people, communities, and organizations. I've had a chance to learn and put these suggestions into practice when working with my wonderful friends on Plasma Pi, which is a core Python package for plasma physics, with the goal of fostering a fully open source software ecosystem for plasma research and education. I also need to give credit to the books and resources that I've learned most of these strategies from, in particular, the book Clean Code by Robert Martin, which I'm holding up to the camera. Well, the resources I'm pointing out are indeed great. They tend to be written for software developers who focus on business applications rather than for students and scientists who focus on research or the broader community of research software engineers. And because of that, I found parts of these books hard to understand because they referred to concepts like business logic and discussed examples that were sometimes pretty far removed from my own research. This presentation is intended for the scientific community. Everything I'm presenting today is under my favorite Creative Commons license, CC BY 4.0. So please feel free to share, remix, and redistribute. I want to start off by saying where I am coming from and where I am not coming from. These suggestions do not come from years of experience writing clean scientific code or following established best practices for writing scientific software. I wish. These suggestions actually come from years of experience writing messy code and then having to live with the consequences. This presentation contains the advice that I wish I could send to myself 19.8 years ago when I was just starting astronomy grad school. So let's get started. If you've spent a decent amount of time working with scientific software, you've probably encountered a number of common pain points. There's often a distinct lack of user friendliness. Scientific software tends to be difficult to compile and install, especially if the software is platform dependent, or if you have to compile and link libraries and mess around with compiler flags. That brings back a lot of memories. These issues are made worse when the documentation is obsolete or even missing entirely. It's often difficult to read and modify code that's been handed to us by someone else. Error messages are often cryptic, which makes errors difficult to debug. Research software is also often inadequately tested, and sometimes the software has no tests at all. Codes are also often closed access rather than open source, which makes our science less open and reproducible. So why do these pain points exist? These pain points exist for a number of reasons, including that programming and research software engineering are typically not covered in science coursework. My thesis was on computational plasma physics, but I never took a single class on how to program. Because of this, scientists tend to be self-taught as programmers. We often learn how to code on our own. My first semester in grad school, I had to learn how to code in Fortran without any help, really. Unfortunately, scientists are often judged by how many first author publications we've had. And because of that, we often write code in a rush so that we can get another paper out the door. All of this time pressure and the pressure to publish prevents us from taking the time to learn. And it's also a recipe for burnout. And on top of all this, software isn't really valued as a research product as much as it should be. So you may have heard about programming paradigms like test-driven development and domain-driven design. I call the predominant paradigm of research software development publication-driven development, or PDD for short. The key elements of PDD are that we measure the worth of researchers by number of publications, which leads us to write code to get articles published. And because of that, we put less emphasis on user-friendliness. We don't get much credit for writing documentation or tests, so we focus on writing journal articles. Funding agencies have historically strongly preferred to fund research projects instead of software infrastructure and maintenance work. It doesn't help that research grants typically last only 3 years. Our communities tend to avoid training and hiring software specialists like research software engineers. And these factors make it so that technical debt builds up over time, where technical debt is what happens when we cut corners in programming now to get a quick solution, but a less sustainable one. The natural consequence of publication-driven development is legacy code. I should distinguish between this PDD, publication-driven development, and a different PDD, procrastination-driven development, which is the time-honored and highly effective strategy of being highly productive writing code while procrastinating doing something else that you don't want to do. But how can we go beyond publication-driven development? One alternative is sustainability-driven development. We'd first create a foundation by covering research software engineering skills in coursework. These courses would cover how to do research using software and how to develop research software. This foundation would allow us to intentionally grow open source software ecosystems for our fields, where a software ecosystem includes software components that work together and grow together. And it also includes documentation, tests, educational resources, and importantly, the communities surrounding the software. We'd value software and data as vital research products, so we'd invest in the long-term health of the research software ecosystem. We'd get into the habit of regularly refactoring code to reduce technical debt. Refactoring is when we improve the implementation of code without changing the code's external behavior. We'd prioritize writing and maintaining documentation, and we'd prioritize continuous integration testing. We might even shift towards executable research articles, which are research articles that have the software and data embedded in them so that readers are able to reproduce the analysis and modify the analysis too. An executable research article would be like a research article based on a Jupyter notebook. With executable research articles, the software would be much more directly intertwined with the article, with the research. Instead of developing code in isolation from each other, in silos, we'd work together as a community to grow the software capabilities that we need. Our communities would have enough psychological safety for us to be able to do that. And we'd value writing clean code so that others can understand and modify the code that we bring to our community. And this brings us to the point of our talk. When we say clean code, what exactly do we mean? For me, clean code is readable so that ourselves and others can understand how it works. Clean code is easy to change. Clean code communicates what the author intends the code to do. Clean code is well tested so that we can have confidence that it is providing the intended results. Clean code has up-to-date documentation that is both concise and complete. Clean code succinctly conveys what the author is hoping to convey. Clean code should be navigable, meaning that we should be able to find our way around it. So functions should be located in the place that we expect the functions to be in. When we look at clean code, we should be able to understand the big picture as well as the small details. And somewhat arbitrarily, clean code should make research fun rather than frustrating. The main takeaway point of this talk is this quote, which is the title of the talk by Stephen Hicks. Code is communication. We write code not only to provide a computer with instructions, but we write code to communicate with our future selves, with future students who may end up using our code, and with future scientists who may try to understand and even build upon our results. So we'll let that sink in. Code is communication. So let's start by comparing two lines of code. My examples are going to be in Python because it was either that or Fortran. The first line says omega CE equals 1.76E7 times B. The second line says electron gyrofrequency equals E times B over ME. The first line uses a symbol for the electron gyrofrequency, a symbol that is probably only familiar to you if you're a plasma physicist. And if we want to learn what omega CE means, a web search isn't going to help. And it's not clear where the numerical coefficient comes from either. The second line spells out the term for the variable, which is great if you want to do a web search. The right-hand side uses standard symbols from physics for the fundamental charge, magnetic field, and electron mass. The second line ends up being twice as long as the first line, but it's quite a bit more readable, in part because of the power of names. So how do we choose good variable names? We choose variable names that reveal intention and meaning, and use names that communicate what the variable actually represents. It's vital to avoid ambiguity. If we have a variable named electron gyrofrequency, does that represent an angular frequency with units of radians per second, or a regular frequency with units of hertz? There's a factor of 2 pi ambiguity there. And does a variable named volume have units of cubic centimeters or bar and megaparsecs? We should also be consistent in our naming schemes. We should use one word to describe each concept and only use that word to describe that concept. We should choose names that are searchable and pronounceable. If we wanted to search a file for a single letter variable like X, we could end up having to scroll through every time the letter X appears in the file. Pronounceable names are easier to keep track of in our minds and also make it easier to talk with others about the code, to have conversations about what the code is doing. Pronounceability also helps improve screen reader or text-to-speech compatibility, which is important for disability access. When we have a choice between clarity and brevity, we should prioritize clarity. Longer names generally work better than unclear abbreviations. It might seem like shortening a variable name would save us time, but it only saves us a few keystrokes. If someone comes across the code later on, an unclear abbreviation might cause them to spend 20 minutes or an hour trying to figure out what the variable actually means. So that's something that I've definitely come across for myself. I should point out that most of these suggestions came from chapter 2 of the Clean Code book, and I'm putting references in the lower right corner of slides. I strive to measure the length of a variable name, not by the number of characters, but by the time needed to understand its meaning. This convention takes into account that most of our time interacting with code is spent trying to understand it or trying to decipher it. The physics community has had a tendency to use short variable names, usually up to about 6 to 8 characters. This practice probably came from the early days of Fortran, when there were strict limits on the number of characters in a variable name or a line of code. And so variable names usually got heavily abbreviated. But by this definition, when we heavily abbreviate a variable name, we actually make it longer because we make it harder to understand. The exception to this rule is for commands that are frequently used interactively, like shell commands. We can also improve the readability of our code by changing numerical values to named constants. Suppose we have the expression velocity equals minus 9.81 times time, where 9.81 is a hard-coded numerical value, which is often called a magic number. But where does this magic number come from? If we're inspecting the code, how do we know it's correct? And what if we go to a different planet? We can clarify our intent by using named constants instead of magic numbers. So this line will make a lot more sense if it's written as velocity equals gravitational acceleration times time. We can improve scientific software by using quantities with units attached to them instead of floating point numbers or integers. If we look at this expression again, what units does the magic number have? Or time, or velocity? Is it SI units or CGS or what? So using a units package can prevent potentially 328 megadollar mistakes. This mistake refers to the Mars Climate Orbiter, which crashed into Mars on my birthday in 1999 because of a mismatch between SI and imperial units in the flight software. An example of a units package in the astronomical Python community is astropy.units, but there are other ones too, like pint. With astropy.units, we take a number like minus 9.81 and multiply it by meters per second squared to get a quantity with units of acceleration. So acceleration has units of meters per second squared. And we can also define a quantity with units of time. And when we multiply acceleration times time, unit operations are handled automatically. And if we try an invalid operation like adding a length to a time, we'll get an error. So it's like an additional really helpful check. Astropy.units is probably my favorite part of the scientific Pythoniverse. A recurring software development strategy is to break down big, complicated stuff into smaller, more manageable, and more reusable parts. The key strategy for doing this in scientific software development is to decompose large programs into functions. Huge chunks of code, sections of code that are dozens or maybe hundreds of lines of code long, are harder to read, to test, and even to keep track of in our minds. Breaking up large sections of code into separate functions helps us to reuse code and improve the overall readability by separating high-level code from low-level details, make the code easier to test, and consequently, because of all this, make it easier to isolate and fix bugs. Decomposing large programs into functions is one application of the rule don't repeat yourself, also known as the DRY principle. A common practice in scientific coding, a practice that I have done quite a lot in my life, is to copy and paste code. Copying and pasting code is fraught with peril. Suppose we adopt a certain section of code as a template and copy it multiple times throughout a project. Then suppose we find out that there's a bug in the code that we just copied. In order to fix that bug, we would need to fix it in every single copy. And if we forget a place that we copy the code, we might not even completely fix the bug. It's better to create functions instead of copying and pasting code. Creating functions simplifies fixing bugs and also reduces unnecessary code duplication, triplication, and quadruplication. To change one thing in a program, we should only need to change it in one place. And don't repeat yourself goes beyond code and data. To quote the pragmatic programmer, every piece of knowledge must have a single, unambiguous, authoritative representation within a system. So how do we go about writing clean functions? To paraphrase Bob Martin's book on clean code, functions should be short. If a function is long, then it's harder to understand and debug. I've started to think a function is long if it's more than, say, 5 to 10 lines. Overall, I suggest keeping functions shorter than about 20 lines, unless you have a good reason otherwise. Functions should do exactly one thing. Functions that do multiple things are harder to reuse, since what if later on you only want to do one of those things? And they're harder to test too. And finally, functions should have no side effects. One possible side effect would be when a function modifies one of the arguments provided to it, or when a function changes a global variable. Hidden side effects can cause confusing behaviors which take a long time to track down. And this means that we should use pure functions when we can. Pure functions depend only on the arguments supplied to them. Pure functions also do not change the arguments provided to it or any global variables. So they are very isolated functions. Functions with complex control flow are harder to read. This slide shows a function that determines whether a particular charge and mass correspond to an electron. If so, it returns true. If not, it returns false. The implementation in this function contains nested if statements. And because of that, even though there are only 2 nested if statements, it takes a while for me to wrap my head around what's happening here. And it becomes even worse when there are 3 or more nested if statements, or when we end up having to deal with more complicated problems. Nested if and else statements and for loops make code harder to understand and modify, and make it much more likely that bugs will slip in, more likely that we'll forget a particular edge case. So how can we rewrite this? How can we refactor the implementation to make it more readable? We can use guard clauses instead of nested conditionals. Excuse me again. To rewrite this function into something more readable. First, we check if the charge is close to the electron charge. If not, we return false, and we're done. If it is close, then for the rest of the function, we can assume that the charge is close to the electron charge as a precondition. Next, we check if the charge is close to the electron mass. If not, we return false. Then, if we make it past this if statement, we can assume that the mass is close to the electron mass hereafter. In this case, we can return true. Using guard clauses like these is a great way to take care of edge cases first to make the subsequent code simpler. And it also helps make the code flat rather than nested. It's important to document each function. Each function should start with an explanatory note, often in the form of a comment at the beginning of the function. In Python, this is usually done via a documentation string or docstring. When we're documenting a function, we should briefly state what the function does. Such a statement can be really helpful should we return to a function after 3 months or even 3 days. We should describe the arguments that are to be provided to the function. What do the arguments mean? What type should the arguments be? Should it be a string or a float or an integer or something else? And are these arguments optional or required? We should describe the value returned by the function, including its meaning and what type we expect it to be. It really helps to include usage examples, especially when sharing the function with someone else. For scientific programming, we should also include additional notes and references. If we're implementing an algorithm from a book or article, we should reference it. It also helps to follow a standard style. For Python, I recommend the NumPy doc style guide. If we follow a standard style, we can often use tooling to take these comments or doc strings and transform them into online documentation. Excuse me, losing my voice. I also recommend checking out the recording and slides from a prior webinar in this best practices series, which was on good practices for research software documentation from February 21. It's number 49 in the archive. Definitely worth checking out. So we've gotten through about half of the presentation, so I'll pause for a moment. Are there any questions?
Yes, Nick. There are questions in the Google in the chat and the Google Doc, but let's take the first two questions here, just for the sake of time. So, how did you justify investing in your personal growth in writing software, given the realities of PDD?
Oh, that is a good question. I think it came about due to frustration with the state of the like community software in plasma physics. So astronomy has AstroPy, and other packages have their own software packages and ecosystems, and PlasmaPy didn't have it. So I ended up getting frustrated and working with people to start this. In terms of how do we justify it, there's also been a push for the nascent field of research software engineering. So one organization that of research software engineers is US RSC, which is worth checking out. And I think part of it we end up having to change our culture, but to some extent that was a bit reckless on not worrying so much about publishing, but rather focusing on the software instead.
Another question here. Can you comment on self-documenting code?
That's something that I'll get to in a bit later. I have some comments on comments, probably my most controversial part of this presentation.
Okay, Nick, let's continue and then we'll address the other questions and then later.
All right, thanks. We'll have time at the end. Okay. All right, so next I want to talk about how to organize high-level code versus low-level code. It's pretty common for scientific software to contain high-level code next to low-level code. For example, we might have high-level calls to the numerical method right next to low-level MPI calls that transfer a variable from one processor to another. High-level code describes the big picture and abstracts away the implementation details, so we don't have to think about them when we're reading high-level code. We can just focus on the big picture. High-level code is analogous to giving a broad overview of what the code does. Low-level code, on the other hand, describes implementation details and contains concrete, specific instructions for the computer. As an analogy, we can think of high-level and low-level cooking instructions. A high-level cooking instruction would be to describe the goal of a recipe, like bake a cake. A low-level cooking instruction would be a specific line in a recipe, a specific direction, for example, to add 1 barn megaparsec of baking powder to flour. It turns out that a barn megaparsec is about 2/3 of a teaspoon. We should avoid mixing low-level and high-level code. When we mix low-level code with high-level code, it becomes harder to understand what the program is doing, and it becomes harder to change the implementation in the code. So we can write cleaner, more organized code if we separate the high-level big picture code from the tedious low-level implementation details. But how do we actually go about separating high-level code from low-level details in a coherent way? We can separate high-level code from low-level code using the step-down rule, which is described in clean code. We can separate the high-level code from low-level code by writing code as a top-down narrative. Suppose we are writing software to perform a numerical simulation. The most general, the most abstract instructions for performing a numerical simulation are to read in the inputs, set the initial conditions, perform the time advances, and output the results. We can make each of these lines into a high-level function, and then break these down into substeps. So for step one, to read in the inputs, we first open the input file, then read in each individual parameter, and finally close the input file. Each of these three lines can become a mid-level function. We can descend another level of abstraction and break step 1.2 down into substeps. And we can create low-level functions for reading in a line of text, parsing the text, and storing the variable. And each of these three substeps could become a low-level function. We're descending one level of abstraction every time that we break up a step into substeps. We're going from high level to low level, from abstract to concrete, from big picture to implementation details. Each high-level function calls only mid-level functions, and each mid-level function calls only low-level functions. Writing code as a top-down narrative lets us separate the high-level big picture code from the low-level implementation details. But how do we go about applying the step-down rule? Suppose we have a long function that calibrates an astronomical observation. It has multiple sections in it for bias subtraction, dark current removal, and eliminating cosmic rays. And each section is labeled with a comment. This function is long, and this function does more than one thing. What if we only wanted to subtract the bias? What if we wanted to do these steps one at a time so that we can inspect the intermediate results? We wouldn't be able to test the individual steps either, so we wouldn't be able to distinguish a problem between the bias subtraction or the dark current removal. So what do? If we have a long function with multiple sections labeled with comments, then we can turn each of these three sections into its own lower level function. So each section of code becomes its own function. Each section name previously given in a comment is transformed into the name of a new function. Our original function becomes 4 lines that describe what the function is doing without needing comments. So in this sense, it's a lot more like self-documenting code. We can now perform each of these steps individually and also test each of these steps. And if we read the new function, calibrate observation, we can get a big picture idea of what is being done to calibrate the observation without having to filter out low-level details. This technique is called the extract function refactoring pattern. This technique is one of my favorite ways to improve code. And again, refactoring means improving the implementation of code without changing the code's external behavior. A quote from the book Design Patterns is program to an interface, not an implementation. There's a lot behind this quote, so let's go through an example from my real research. Suppose we're writing a program that makes heavy use of atomic data. We start out by using the Chianti atomic database, but eventually we decide to switch to the AtomDB database, which is pretty similar, but we want to do cross-checks. Then suppose our high-level code repeatedly calls Chianti directly. If that's the case, then switching to AtomDB will be a pain. And we'd have to change every single call from Chianti to AtomDB. On the other hand, if our high-level code calls functions that call Chianti, then we would only need to make these interface functions call AtomDB instead. We'd only need to change the code in one place. And because we'd only need to change the code in one place, our high-level code can remain unchanged. It's pretty common to find ourselves in situations like this when we engage in scientific programming, like when we want to interchange one algorithm with another, or one data source for another, or a bunch of other things. So it does come up pretty often. These interface functions in this example are an example of a boundary. Putting well-defined interfaces, well-defined boundaries into our code lets us break up huge, complicated problems down into smaller, more manageable chunks. By putting boundaries between our high-level code and low-level data access code, we're able to make our code a lot more flexible and a lot more maintainable. We can put a boundary between stable and unstable code as a way to manage complexity. Even if part of our code base is relatively clean, it's not going to be stable if it depends directly on unstable, continually changing code. The alternative is for our clean, stable code to depend directly on the boundary, on the interface that separates the stable code from the messy, unstable code. The clean code then only depends indirectly on the continually changing code. When we do this, it's important for the boundary itself to be stable, so that our clean code can be more stable. So we want to keep the positions where the messy code meets the clean, stable code. We want to keep those interfaces stable. And it turns out that it was really fun to draw this figure. When designing software, it's important to strive for high cohesion and low coupling. Cohesion is the degree to which the contents of a module belong together. It's a measure of how related different functions are within a module. Our code will be better organized and easier to maintain if our modules have high cohesion. Coupling is the degree to which the contents of a module depend on other modules. If two modules are highly coupled, highly interconnected, then it's harder to update code inside one module because you might have to make related changes in another module. Decoupling code reduces the overall complexity of that code. Code elements that change together at the same time and for the same reasons belong together. If we want to update how something is implemented, it's a lot easier to do so if all the sections of code we need are all in one place. It'd be easier if we had to modify code, it would be a lot harder if we had to modify code if it was spread out across a bunch of different files. Similarly, we should separate code elements that do not change with each other from each other. So now we've gotten to my most controversial slide. The piece of advice that was most surprising to me revolves around the fact that comments are not inherently good. But don't get me wrong, there are times when a well-placed comment can be really helpful and save us a lot of time and frustration. But as code evolves, as we continue to work on a program, comments too often become out of date, begin to contain misleading or incomplete information, or get displaced from the section of code that the comment corresponds to. There's even a quote that a comment is a lie waiting to happen, and that definitely warrants cat emojis here. This quote is actually pretty worrisome for those of us who have engaged in scientific programming for many years. I found it quite disconcerting to realize that well-commented code is not synonymous with well-written code. And there are certain classes of comments that are often unhelpful. For example, commented out code. Commented out code that's left in the code base over time quickly becomes irrelevant as the surrounding code evolves, which can cause confusion about how the commented out code fits into the program. Like, why is it there? So it's often better to use version control instead, like with Git and GitHub or GitLab. Version control lets us look back on old versions of code in a way that preserves the context. We should be cautious of comments used to define variables. it's often better to encode definitions in variable names instead. For example, suppose we had a variable named tau that represents torque. We use a comment to state that tau is torque. What if we renamed the variable to torque instead? We'd remove the need for the comment and probably make the subsequent code more readable. And this is another example of self-documenting code. But we can still use a comment if the definition is complex, or if there are nuances, or if there's important contextual information. So that's something we can definitely use our judgment to decide upon. Redundant comments clutter up the code without providing any additional information. If a line of code is straightforward enough to understand, like I equals I plus 1, and having a comment for increment I, we don't need that comment to explain what it's doing there. There are times when comments can be extremely beneficial for scientific programming, though. And there are a number of helpful commenting practices that we should keep in mind. The first practice is to prefer refactoring or rewriting a section of code over explaining how that section of code works. We should make it more self-documenting. If we find ourselves thinking about commenting on a section of code, we should ask ourselves how we might rewrite the section of code so that it becomes more understandable without comments. Sometimes using a more descriptive name will suffice, or maybe extracting that section of code into its own well-named function. Ideally, we'll be able to use the code itself to communicate what the code is doing and remove the need for the comment. But at other times, we might decide that even after refactoring, it really does need a comment, and that's fine. We can use our judgment to decide that. The comments are doc strings that document a function should explain the intent of a function, such as what the function does and why, and how it fits into the big picture of the code. Comments and doc strings should also explain interfaces, like how a function is used and what the arguments to it are. Comments should emphasize or amplify important points. And comments can be used to describe why a particular seemingly obvious approach was not used. Comments can provide context to describe the big picture, as well as references in the literature that discuss that particular algorithm, or we can include links to Stack Overflow pages, for example. If we're writing code that will be read by students and scientists without formal software training, then we can use comments to describe software engineering concepts that they may be unfamiliar with, or at least give them the terminology to help them look something up. If code will be read by research software engineers without training in your scientific discipline, then we can use comments to describe the relevant scientific information. This information often works better in online documentation rather than in comments, though. And finally, it's vital to update comments when updating code. The biggest danger of comments is that they become out of date or misleading. So it's important to keep them updated. And if possible, we should write comments in a way that they are unlikely to become obsolete even when the code changes. We should try to make our comments timeless, which isn't always possible to do, but it's helpful to do when we can. Clean coding requires balancing competing priorities or trade-offs. For example, we often have to balance readability with computational efficiency. Readability is usually much more important than computational speed. And this is because computers are fast and getting faster, and that our time is significantly more valuable than a computer's time. This doesn't apply so much towards exascale computing, I do have to say. But for an extreme example, a 10-fold improvement in time is completely irrelevant for code that takes a millisecond to run and is only run occasionally. We could take an hour to optimize it, but we'd only save a few processor seconds per year. if that. If the code becomes less readable, then making these changes could result in needing even more of our time to understand and change the code in the future. But with that said, there are times when optimizing code for performance is vital. We should optimize code only when necessary, only after the code is working correctly, and only after using a profiler to identify the bottlenecks, the places where the code is spending most of its time running, which might not be in the places where you expect. It's important to avoid premature optimization, but we should still plan ahead. We'll often have some idea of where the most computationally intensive parts of our program will be. If we start out by implementing an algorithm on one processor core, but we know that we'll eventually need to parallelize it, we should keep this in mind. For example, it can help to put boundaries that separate the code that will eventually need to be optimized, the kernel, from the code that probably won't. So essentially to isolate the code that we'll need to optimize in the future. So we've now spent a while talking about writing clean code, but writing clean code takes effort, which was alluded to with one of the questions earlier. But this leads us to a question. When should we invest time in writing clean code? When should we put in the extra effort? There are some clean coding habits that save time relatively quickly, such as writing short functions that do one thing and writing tests that can be run automatically, as opposed to testing code interactively or not testing code at all. Some other practices, like choosing descriptive names, often don't take much extra time once we get into the habit of it. If we're interactively exploring a data set, it's typically not worth putting that much extra time into writing clean code. It is worth putting extra time into writing clean code if you'll reuse the code, maybe weeks from now, days from now, or years from now, or you'll be sharing the code with others. The more likely it is that the code will be read by others, the more worthwhile it is to write clean code. It's important to avoid perfectionism. Our goal is to write readable and modifiable code, not to write beautiful and flawless code every time. And it's important to remember that writing clean code is an iterative process, and talking with other people about code is really helpful with that. So it's better, I'd say, to mostly but not completely follow the suggestions I'm providing to you. So here are my final thoughts before questions. It's worth thinking in terms of trade-offs and competing priorities. My suggestions for writing clean code balance trade-offs in a way that works well most of the time, at least in my own experience. There will be times when the trade-offs are different. A longer and more descriptive function name might improve readability, but long names are bad for shell commands like ls that we use maybe 50 times per day. So there's a trade-off between readability and ease of use too. When faced with situations where the trade-offs are different, it might end up being better to take a different approach from some of my suggestions. So it's important to use our own judgment. A recurring theme is to manage complexity by breaking up big, complicated code into smaller, more manageable chunks that are at least somewhat isolated from each other. We do this by writing short functions that do exactly one thing with no side effects, preferably pure functions, and by separating high-level, big-picture code from low-level implementation details. The main takeaway point is that code is communication. We write code not only to tell a computer what to do, but also to communicate with the people who will be reading our code in the future. Along these lines, we need to remember the importance of community. We don't write research software in isolation from each other. We make use of software others have written, and we share software for others to use. So we shouldn't forget community. And in order to have an environment where we aren't made to feel shame about sharing imperfect code, we need to foster psychological safety in our workplaces and places of learning. So psychological safety is the shared belief that one can express ideas, take risks, and be vulnerable within a group without fear of negative consequences or judgment. It's been described as permission for candor. How to build psychological safety into a research software community would be a great topic for a future best practices webinar. I also recommend the book, The Fearless Organization by Amy Edmondson. And finally, please download these slides for special bonus content, which is on writing error messages and also writing clean software tests, since that would have taken me another probably half an hour, 40 minutes to go through. And also, it's really helpful to check out the archive of past best practices webinars too. There's some fantastic stuff. All right, and with that, I'm ready to take questions, and then after that, to take the rest of the afternoon off. So thank you all for being here.
Okay, Nick, yeah, thank you. So yeah, there are questions here. I'm not sure if we'll be able to go through all of them. I just like to remind the participants that we'll put these questions in a kind of question and answer document and send it to everybody. But there is a long question here. So let's see, Nick. It goes like this. So the benefits of longer names are well explained in the slides, okay? But so when someone is dealing with long variables names in the code, when they're part of a long complex equations, that can be a problem. For example, taking an equation from a paper, and that may introduce errors, and this can be challenging. And then what about using Unicode for variable names so that they can use the same symbols as using associated theory, manual, or paper?
This is a fantastic question, and I've thought about it a lot. I really like using Unicode for variable names. The difficulty is that it can make it difficult for others to read the code, or sorry, to write the code if they're using that. So when we want code to be easy to change. If we are transcribing an equation from a paper, putting it into code, and we want to be able to check that equation, make sure that it's correct, then using the symbols in the paper in the actual equation can be really helpful. So it depends. For the most part, for equations of reasonable complexity, I prefer spelling out the variable names, but for more complicated equations, it's definitely a reasonable choice to use Unicode variables. So yes, thank you again.
Nick, another question here. Do short and searchable variable names like loop indices, IJK, have a place in scientific software?
Not many places. I think using short loop indices, that can be reasonable for short loops, but having a more descriptive name is often better. If we have standard symbols for things, like capital B for magnetic field and plasma physics, that's a universal symbol almost. That I think would be fine, but we should be very careful about using that.
Okay, so another one here. Wouldn't the requirements for readable code be fulfilled in proper documentation of any given code base?
So one thing that's tricky is when the documentation is separate from the code that it's referring to. So in Python, the doc strings contain the description of that function. So I don't think it's a replacement for the proper documentation, but having proper documentation about it, like if a project has a good contributor guide, that can be really helpful, but I don't think it replaces the need for readable code.
Okay, so there are more questions here, but Alex, since you had raised your hand, would you like to ask your question?
Sure. I just typed it because I thought we were going the other way.
Ah, okay.
So when I write a paper, I use symbols. I use M sub E. I don't use electron mass. And why isn't that the right thing to do when writing a code? One could have a table of these things at the beginning if there's some ambiguity. But it seems to me if you're checking over an equation to see if you've done it right, having electron mass times something makes it basically necessary to take a pencil and paper, turn it back into symbols in order to check it, and far more cumbersome. So, at some level, yes, it is ultimately more understandable in that it, really defines things, but it's unusable when you're trying to say, did I use the same equation as my colleague? Was that really what was intended? Is that why we're getting different answer? Having some compromise seems to me a sensible thing to do in a particular context, especially if the context is well established.
Yes, these are all really good points. And it depends on, as you said, the complexity of the equation. I think for the next time I give the talk, I'm going to include that. So thank you for everyone who's brought this up. Yeah, I think it's something you do have to balance trade-offs. The reason why I'm hesitant to use variable names or variable symbols is when people are going to come across the code and not be familiar with that particular symbol. And it also makes it harder to do web searches for that symbol. But having a table at the beginning can be really helpful, but it's important to do this consistently throughout the project.
Yes, and some set of standards would not hurt, especially within a field.
Yes, yes, very true.
Might be the Earth mass in a different context.
Exactly.
So as I said before, all these questions will be, I'll ask Nick to go through them and here in the Google Doc, but I'll take another one here for you, pass another one for you, Nick. I find that code where high performance is crucial makes following clean code guidelines difficult. Talking about code that runs for a couple million CPU hours, so optimization is important. Do you have any tips for how to find a balance?
That is tricky. It depends on what the trade-offs are. Figuring out the most computationally intensive parts. It's those parts where the high performance is much more important than the readability, though both are important. And I think another tip would be think about using a programming language which has better readability. So I'm usually firmly in Camp Python, but I really like Julia also because it combines really high performance with a lot better readability than Fortran, and at least the code that I've written. So yeah, in the end, it's about figuring out the trade-offs.
Nick, another question here from the Google Doc. Do you have an opinion on groups like software carpentry that teach this sorts of skills?
They are awesome. I really like software carpentry. Probably a software carpentry workshop in 2016 was what set me on the path to giving this webinar now. So software carpentry is fantastic.
Can you talk more about another one here. In writing code for data analysis, do you have tips for documenting naming code for linear algebra, like tensor sizes and operations? In my experience, the participants' experience, these area tend to be under-documented and under-tested since it's more difficult.
The short answer is no. But if anyone from the audience does have suggestions for that, please feel free to answer in the Google Doc.
Can you talk more about the role of testing? How do we balance the time writing tests versus the time writing the functionality of our code?
Software tests are the best thing since sliced arrays. So I say that my belief is that writing tests saves us time. Whatever code we write, we are going to have to make sure it works. And if we don't write tests, then often we'll end up checking the code manually, like doing it interactively. And that's pretty time consuming. So tests, it's as important to have good, clean tests as it is to have clean code. So software testing is vital.
Final question here, Nick. What are your thoughts on literate programming?
I'm not so familiar with the concept. I've heard it a bit, but I don't know if someone want to define it.
Is the participant who asked that question in the Google Doc still with us? Maybe not. So, so again, for the sake of time, I see there are some questions that remain unanswered, but Nick will go through them, right, Nick? And we'll send a clean version of the Google Doc to everybody who signed up for today's webinar. So, and also I'll be taking the comments here and putting them into the Q&A and try to find a way to organize them. Thank you for putting all these comments in the chat, folks. Nick, thank you very much. Thank you all the participants for joining, for supporting, this webinar series. Thank you very much.
Thank you all.